Hey guys, welcome. Today we're looking at Saxon Advanced Math, and we are doing lessons 20 through 23. So that's what we'll be covering this week. So I wanted to spend some time with you guys looking over that today. Okay, so lesson 20 starts out with two special triangles. Now you might remember going over this a little bit in Algebra 2, but also in geometry. So what I really love about this lesson is its shortcuts. So I think the great thing about shortcuts is it's not encouraging us to be lazy. It's encouraging us to conserve brain power, right? So anything that can help us find a neat little trick or a quick way to solve something, I'm all for, right? So what are some special triangles? Well, first of all, from right triangles, we of course know we understand our a squared plus b squared equals c squared, right? These are our legs, and then this would be our hypotenuse. Hypotenuse is opposite the 90 degrees, or we call that right triangle, right? So we of course remember our Pythagorean theorem. That's one of our best friends in advanced math and also geometry. So that's super important. Now, what about some special right triangles? Well, a special right triangle would be what we call a 45, 45, 90 triangle. So let's talk about what that means. 45, 45, 90. Well, we know every triangle has 180 degrees. That's given. So 45, 45, 90 means that the two legs have to be the same. Why do they have to be the same? Well, because every triangle is 180 degrees. So if I'm taking away the right triangle, all that would leave is 90 degrees left over, right? So if I have a right triangle, I know that the two other legs, the sides opposite those two legs, have to together equal 90 as well, because then with the right triangle, it will together make 180. So if these two are 45, 45, then I understand that it has to be an isosceles right triangle, okay? So that means that the legs are going to be congruent. So a 45, 45, 90 is very special because I immediately know the legs are the same. It's just like a light bulb comes on. 45, 45, 90, legs are the same. So a shortcut for that is I would call this x, and then this would be x square root of 2. Miss Kim, how did you know that? I'm glad you all asked me that. You're probably not asking me that at home, but it makes me feel good to think that you might, right? So if I know that the legs are the same and it's a 90-degree triangle, then I know that the hypotenuse has to be x times the square root of 2. And I know that because I also know the Pythagorean theorem, a squared plus b squared added together is the square root of c squared, right? A squared plus b squared equals c squared. So that's already been done for me. So this is just a shortcut. If you memorize this, it will make life easier. So if I know that x is 9, then the other leg also has to be 9 if it's a 45, 45, 90. So if this is 9, this would be 9 square root of 2. So it just makes life so much easier. When you're taking those ACT tests and you're under a time crunch, if you figure out that it's an isosceles right, you can quickly say, well, if this leg is this, then this has to be the other. Then multiply it times the square root of 2. That's my hypotenuse. It took you, 15 seconds? You only have 60 minutes to do 60 problems on your ACT. So imagine how much time this shortcut will take, and then you can use that extra brain power on other advanced problems, and you'll be able to hopefully score higher on your ACT, and it'll really help you plug that in when you're doing standardized tests. So a squared plus b squared equals c squared. Shortcut for 45, 45, 90 would be x square root of 2. You'll find that on the bottom of page 145 of your Saxon Advanced Math book. All right, and it shows you the sine, cosine, and tangent, but I've just pointed out to you the most important part. Now, what's another? So, Miss Kim, you told me that there would be two special right triangles, so I'm super glad you asked. All right, so another right triangle that we're going to look at would be a 30, 60, 90. Now remember we talked about that every triangle has 180. If one of them is a right triangle, that's 90 degrees. That leaves 90 for the other two. Well, we've talked about 45, 45, but what if we divide up this 90 instead and look at 30, 30, 60, 90, right? So that's what this triangle down here would look like. All right. So what is the shortcut for that? Well, I'm really glad you all asked me. So opposite the 30, we would just call it X. And then I'm looking on page 146 at the bottom. So if you all want to look there as well. So opposite of the 30 degree would be X. And then opposite of 60 would be the square root. It would be X square root of 3. And then opposite the 90 would be double whatever the opposite of 30 was. So we'll call that 2X. Now your book doesn't put the variable in it, but just so you guys understand, it's whatever that is. So if they tell you that X is 2, if the side opposite of 30 is 2, and you know it's a 30, 60, 90, then I know if X is 2, then this would be 2 square root of 3 opposite of 60. And the hypotenuse, if this side was 2, the hypotenuse would be 4. It's double whatever that is. So there's some really great things that you can do with that. They're showing you the sine, cosine, and tangent. Remember how we talked about sine, cosine, and tangent last year? Saw, ka, toa. And we did that in Algebra 2 as well as geometry. We did it in both of those. So saw, ka, toa. Sine, opposite over hypotenuse. Ka, the cosine, is adjacent over hypotenuse, and tangent is opposite over adjacent. I'm not going to spend a lot of time over those just because you can take the time to say if I'm standing at the 60 degrees, the opposite would be x squared of 2, adjacent would be x. Or, if you're doing the sine of the 60 degrees, the sine of 60 is opposite over hypotenuse. So you guys can certainly do more in depth with that at home, but I did want to point out to you those special triangles. So we've got our 45, 45, 90 and our 30, 60, 90. So both of those are really important. They're great shortcuts. And I'm all for never should we be lazy, but I think shortcuts really make our day. So I love a good shortcut, and I think it really is a great way to solve something and kind of use that time for something a little more difficult. So your book is showing you on the top of page 148, draw the necessary reference triangle and evaluate. So they're telling you the tangent of 45. So they work that out so you can see what those parts are. So they figured it out to be 2 square root of 5 based on that, because we know that if it's a 45, 45, 90, then we know that the legs are the same. So we can think through that. If it's saying that the tangent of it would be opposite over adjacent, then all we need to do is simplify it. All right, so 10 over the square root of 5. So, of course, we can't have square root of 5 in the denominator, so we're just rationalizing that denominator, no square root of 5. So that's all we need to do there in that problem, since the legs are the same. All right, so that's problem, that leaves you to problem set number 20 on page 148 and 149. So if you guys would, this week, you're doing the evens on those sections. All right, let's move on to lesson 21, evaluating functions, domain and range, the type of functions, and the test for functions. Wow, that's a lot to go over. The great thing here is, friends, they're just reviewing all the things that we have studied before. Now, advanced math has been a while since we had Algebra 1, but you studied functions a lot in Algebra 1. What is a function? Well, the thing that I love about math is absolutes, right? There's a lot in this world that I can't always depend on. This might change. Gosh, inflation, prices are always changing. But one thing that I can understand in math is that for every input, there's exactly one output, right? Our input directly relates to our output, right? Same in advanced math. What you put into the class is what you're going to get out of it, right? Same is true in future jobs that you have, relationships, whatever. Your input directly relates to your output, right? If I don't put any gas in my car, I'm not going to have much output with that car, right? So I've got to understand that a function is the input, relating to the output, all right? So we're starting on page 150, the bottom, lesson 21. So it's talking to us about a function. And they show you, they give you, and it's not an equation, it's an expression because it doesn't have an equal sign, right? Now they give you the function down below, y equals x squared minus 4x plus 7. So we have a quadratic function. Ms. Kim, how do I know it's a quadratic? Because it's x squared, right? What's the shape of a x squared function? Or we call that a quadratic. Well, that's a parabola, right? And the parabola opens upward. If the x squared is positive, it opens downward if it's negative. We did that in Algebra 2 last year. So I hope you'll remember that. Independent variable and the dependent variable. What's the difference there? Well, you guys know when you were younger, you were dependent on your parents, right? As you're growing older, you're becoming independent, right? You might have a job and you're starting to take what you're earning and you're starting to become more and more independent, right? So if I say y equals x, right? So we know that from Algebra 1, that's just a linear equation, y equals 1x, right? So whatever y is depends on what x is. So x is my independent, y is my dependent. Okay? Now we can write it in function notation. So they show us that there. F of x equals, and then we could have whatever. Say I had they did a quadratic, they even did a cubic, but say I had 2x minus 3. Well, I'm just writing it in function notation, right? I'm not sure if you can see that. So that's f of x equals 2x minus 3. We're just replacing the y with f of x. So it's just saying the function of x. When, and it's telling us this, right? So we're just replacing the y. That's my dependent, right? My independent is x, whatever I plug in that value for x. And I can make a graph for that, right? So I can say when x is -1, 0, and +1. And I can plug those values in and see where it would chart. Now, to prove that it's a function, I would have to show that every input has exactly one output, and that's what I want, right? So if I ended up having a graph or a set of ordered pairs, right? And I said 1, 3, 2, 7, 8, 12. I have no clue what this graph is going to look like. I just randomly picked out some numbers, right? But 1 is 3, 2 is 7, 8 is 12. That is a function, right? Because every input has exactly one output. What if I changed this 8 and I made it 1? So 1 up here was 3, but then down here 1 was also 12. Friends, that is not a function. It cannot be, because I can't plug in 1 one time and get 3, and another time 1 is 12. That's not a valid function, right? Because every input didn't have exactly one output. So we would say that is not a function. You know, scientifically speaking, and it's great because the way that we look at science, the language of science is math. You see that in physics and chemistry. All of those maths are dependent on math, right? Could you imagine signing up to take a medication or something that sometimes you plugged in this way and it came out this way, and sometimes this, you want to make sure, no, it should be, the results should be valid. It should show a function that when I do this, it comes out this way, it comes out this way. I don't want it to come out different ways, right? So that's not a valid function. All right. So for every input, there's exactly one output, right? So that's one thing we're talking about in lesson 21. To evaluate the function, we plug in our variables and then see how they come out. So we would make our table there. All right, so they're showing you that. Look on page 152. So what is the domain and the range? Well, the domain is the input. The range is the output. So if I were to take my function up here and plug in -1, So negative 1 times 2 is negative 2 minus 3 is negative 5. So 0 times 2 is 0 minus 3, negative 3. 1 times 2 is 2 minus 3, negative 1. So what I did is I just took this function, I plugged in my inputs, my x values, and I got out my y values. Just a quick side note, are you copying these notes at home or in class as we're doing them? Don't forget that your notes count as extra credit. So I want to see this in your notebook, because when you go home to solve these, you're going to say, oh, I forgot. What did we say about functions? And make sure you have that on there. And then every input is exactly one output. So that should be in your notes. So help me out with that. All right, so domain is the x values. Range is your y values. So if I were to say, hey, what's the domains of your function 2x minus 3? Then you would say my domains are negative 1, 0, 1, etc., right? And you could do the same for range. So this is a very simple, this is an algebra 1 type problem. So you understand as we get further along in advanced math, our domains and ranges are going to be a lot more complicated, but I'm just wanting to take us back to our algebra 1 roots, right? So you can look on page 152 and 153, and it talks a lot more about our domains and our ranges. Notice that your book uses it uses range. It gives, and it also has domains. So there's kind of they also do this for real numbers. So each textbook has kind of different ways that it notates things, and you all need to make sure you're very familiar with that, especially for standardized tests. All right. So it shows you range and domain on page 152, 153. And I want to encourage you, make sure you take time to read over. And I don't have time to read the examples out loud to you. I'm just going quickly over these concepts and especially the terminology, because I want to make sure you remember and draw to mind these terms as we've had a long break. And so some of those terminologies are not as fresh in your mind, so that's important. All right, if you look at the bottom of page 153, domain and range becomes important, especially we're looking at a graph at the bottom of page 153, and that's a square root function, right? So it's going to have a definite beginning point because at certain places it's not a real we understand that we've talked about imaginary numbers. So let's see, on example 21.7, it says the square root of x plus 4. Well, I can have negative 4 plus 4 is 0, but if I had negative 5, then I would have negative 5 plus 4 would be negative 1. So the square root of negative 1, we understand as an imaginary number. Now, we've talked about that in Algebra 1, but that's not part of our graph. That's so our graph would start at negative 4. Everywhere else would be undefined, right? All right, so that's the bottom of page 153. So look on page 154. We're talking more about domain and range. You understand on example 21.8, you've now we're looking at when I have an asymptote, right? So if you look at the graph in the middle of page 154, that is the graph of the square root of x over x minus 2. So you'll notice the denominator. My denominator can never be 0 because it would be undefined at 0, right? If I have a number divided by 0 and I plug it in my calculator, your calculator fusses at you and says undefined, undefined. So anytime I have the graph of a fraction, I need to make sure that there's an asymptote at whatever would make the denominator 0, because I can't have that. So you'll see the picture in the middle of page 154. It's a dotted line going through 2, because I can't have 2 minus 2 is 0. That would make the denominator 0. So we call that an asymptote. And in this case, it's a vertical asymptote at 2, and both sides of the graph approach that asymptote, but it will never be 2. It will approach it. It will come extremely close to it. 2.0001, but I can't have it at 2, right? So that's why we call it an asymptote. It will approach it. All right, 21.C, it's talking more about functions. So every input has exactly one output, and we've talked more about that. Look at page 155. It shows you, now one thing I want to point out to you on page 155, it shows that you can have two numbers that both come out the same. That is a function. Now, our brains sometimes say, well, wait a minute. But remember, every input can have exactly one output, and they both can have the same output, but you can't have the same number come out differently. So I hope you'll file that away and just make that really concrete in your mind. So if you look at the difference of this one in relationship to the next one, in the next one, 4 came out as both 3 and 5. That's not a function, friends. So we would say not a function. But the first one is a function, right? Because different numbers can come out the same, right? It is a function. All right. Look at the bottom of page 155. We use the word function to describe a mapping from each member of the input set, which is called the domain, to exactly one member of the output set, which is called the range. Each member of the domain maps to an image in the range. So I like it just easy to say every input has exactly one output. Okay? There's a lot of boldface in there, so I hope you'll take time to read over those examples because I feel like that's very important. Now, we have done tests for functions, and we call that the vertical line test. So if I were to draw a circle, I understand that that cannot be a function. And the reason for that, it is a relation, but it is not a function because it passes through the vertical line test twice, right? But if I drew a parabola, we understand that that is a function because every time I draw a vertical line, it's going to pass through it exactly one time, right? So that is a function. And they drew a cubic function because it was not just a parabola, it turned twice, right? So they drew that at the bottom of page 156. All right, the horizontal line test, let's talk about that. At the top of page 157, if we are given the graph of a function, we can determine if it is a one-to-one function through a test called the horizontal line test. So this is new to us. We did not have this in Algebra 2. So the horizontal line test, a function is a one-to-one function provided that any horizontal line intersects its graph in at most one point. So look at, I've got first the graph on the left on page 157. Notice when I do the horizontal, it only goes one time through. So we know that is a one-to-one function. But notice the parabola, notice that the horizontal line goes through it 2 times. Now it is a function, but understand that the y can come out 2 different, I can plug in a number and it can come out the same for, say, +2 and -2, because remember that a parabola, if I fold it in half, it's going to mirror itself. So that's why it's not a one-to-one. It is a function, though, but it's not a one-to-one just because sometimes the positive and negative can mirror itself in a parabola. So a parabola is not a one-to-one function. And the horizontal line test is the one that we would use for that. The function line test that we would use is the vertical line test. And we did that in Algebra 2. I believe we actually talked about it at the end of Algebra 1. But that's been a while back, my friends, hasn't it? All right, so that's the end of Lesson 21. Lots of terms there and a lot of pages. So I know it's really important. I do want those terms, the bold-faced terms, need to be in your notes. All right, so that's part of your homework along with the problem sets. In advanced math, we don't have any practice problems, but you do need to have those terms written in there. So count those as your practice sets, my friends. All right, so lesson 21 is in the books. Lesson 22, absolute value and reciprocal functions. So we've got 2 lessons left. Absolute value, what is that? Remember those bars that come up and we say the absolute value of a variable, right? So if I plugged in 5, the absolute value of 5 is 5. If I plugged in -5, the absolute value of -5 is also 5, right? And absolute value has no negative value. And the reason is absolute value is just measuring the distance something is from 0, right? So think of driving your car. Doesn't matter whether you go forward or backward. It's going to use the same amount of gas, whether you're in reverse or not. Please don't go on the interstate in reverse. But you're still going to need gas, right? And a good rear view camera. But please don't do that, all right? Just when you're backing up, just understand that the distance that we travel is absolute value, right? All right, now distance can have direction. And so sometimes when we're talking about the direction of something, sometimes they'll do north is positive, south is negative, or, something like that. So it can have direction, but the absolute value of it is think of it as it's the amount that I go, right? Not necessarily the direction. So page 160, 161, and 162. And then our problem set starts midway on page 163. So again, there's a lot to look over on this. So we remember the absolute value, I can graph it. Your book shows you the absolute value of x is greater than or equal to 0. Remember the greater than is greater than or less than. Let me write this down. Greater than or less than. Those two symbols. So greater than or less than is going to be an open dot. And then greater than or equal to, less than or equal to is going to be our closed dot, right? Because just remember the or equal to means that it's including that point. When it's greater than or less than, it's up until that point, but not including it. So when you're graphing it, I always just think of these symbols have a little bit more pencil, lead, or ink that I have to use. So you have to use a little more pencil, lead, or ink to fill it in because it is including it. All right, so those are some important reminders. That's on the middle of page 160. You'll see the difference between the solid and dotted line. So that would be a great review question, is absolute value, whether a line is dotted or solid. So maybe that will be on your assessment this week. All right, and make sure that if you have questions on your assessment or homework, make sure after the video that you all spend some time reviewing over those to make sure you're fresh for next week as well. So the book is showing you the absolute value that is less than 4, and they're pointing out to you the absolute value that is greater than 4. Notice it's an open dot because it's not including it, and then when it's less than 4, it's going to be up until 4, but not including 4, and then everything inside of it. When absolute value of x is greater than 4, it's not including 4, but it's going to be everything after it. So an example is -6. The absolute value of that is 6, and that would be greater than 4. So that would be one solution. All right. Then they show you the graph when you also have another, like if you have x minus 2 or x plus 2, how to solve those. So we've done that in Algebra 2. We actually did at the end of Algebra 1 as well. So all of that should be review on page 161. I'm not going to spend a lot of time on that, but you do need to graph those on a real number problem. So let me just review over, let's see, how about example, let's see, example 22.3, it says graph it all the, so we're looking at the real number values of the set that include absolute value of x plus 2 that is greater than or equal to 3, right? So what does that look like? X plus 2 absolute value is greater than or equal to 3. So I'm writing that down. I'm sorry you can't see that while I'm writing, but absolute value of x plus 2 is greater than or equal to 3. Do you know what kind of dot we're going to use? I hope someone said it so I can give candy. Is it an open dot or a closed dot? That's right. Closed dot, because it's including it. I have to draw a little bit more lead. So somebody needs candy there, right? All right. So how am I going to graph that? Because it's greater than or equal to. So greater every time I think of greater, I always write or, greater or. I just try to think of like the element iron ore. I just think of greater or, less is including, less like land, less and land, less includes it, greater is or. So I'm going to move this down to the right side and just recopy it. X plus 2 is greater than or equal to 3. Now I'm going to come down here over on this side and write x plus 2, and I'm going to flip the symbol and rewrite it with the negative value. So I put or in the middle. I'm going to circle that so we remember, and we're just going to keep bringing down the or. Now I'm going to solve both equations. So I'm going to subtract 2. So x is less than or equal to negative 5, or over here I'm going to subtract 2. So x is greater than or equal to 1. So when I graph it, look at the picture that they have in the middle of page 161, and I'll graph it down here. So I've got 0, 1, 2, 3. Now I've got negative 1, negative 2, negative 3. Oh, I'm going to have to make my line keep going, aren't I, friends? Negative 4, negative 5, negative 6. Sorry, I didn't balance that well, did I? All right, so what kind of dot would I use at negative 5? We already said closed dot, and it's less than, so it's going to keep going out deeper into deeper in debt, so my line is going this direction. And then x is greater than or equal to 1, so I'm going to put a closed dot at 1, and then it's greater than that, so it's going this way. So it's a greater is or, so they're going to repel each other, right? When it's less than, it's and they join each other. So all of this is bringing back a little bit from our Algebra 1 and Algebra 2 days, and I know we've had a long summer in between, so hopefully that's a good review for us. And again, it is at the closer to the lower half of page 161. So you can take a look there. Now, sketch the graph of the function y equals the absolute value of x. So you know that is when y equals x, that's linear, so they show a picture there. All right, so that is on page 161. Turn and look at page 162, reciprocal functions. So if the original function is y equals x, the reciprocal function y equals 1 over x. The reciprocal means inverted or upside down, all right? So a vertical asymptote is a vertical line that is approached by the graph of a function as x approaches a fixed point. The graph of a reciprocal function has a vertical asymptote at every place where the graph of the original function intersects the x-axis. So they're explaining that to us and showing us the reciprocal functions. Now, I do not think that we've done that before, so that is new to advanced math. So they show you, even like example 22.5 on the top of page 163, they're showing you the graph of the function y equals 1 over x squared. So you're going to have a vertical asymptote there as each of those approach the y-axis there. So they're showing you that. All right. So you have no practice problems on those. They're just showing you each of those different graphs. And the great thing about that is you're just plugging in your inputs and your outputs. So that's your reciprocal functions. All right. Then the last lesson, lesson 23, is going to be exponential functions and sketching exponentials. So let's talk about that a little bit. So we've done in Algebra 2, we did do some exponential function. It was more toward the end of Algebra 2. So don't forget what we call powers, right? They're just showing you when I have x to the 5th, right? That's going to be our exponent. X is our base. Our exponent is going to tell us how many times I multiply my base. So that'd be x times x 5 times over, right? I'm going to have to put the pen down, right? X, right? So I've got 5 of them. So the book also shows you, like, if I had 3 squared, that's the same thing as saying my base is 3, so I have 2 of them, so it's just 3 times 3. So that's just taking it back to the Algebra 1 level, right? Now, what they're explaining to you is, how about when I have variables as the bases, or if I have a base and I have the exponent as a variable. So they show you, what about when I have y equals 2 raised to the x? And we did graph that in Algebra 2, so I hope that calls to mind some things that you remember. A couple of things that they point out, and I think they don't point it out until, so the top of page 168, they're showing you different functions there. And I want to draw your attention to that, because on page 168, y equals 10 raised to the x, y equals 3 raised to the x, y equals 2 raised to the x, and then y equals 1/2 raised to the x. What can you notice about that? Well, notice that the only thing that changed on all of those equations, there were 4 equations on the left graph on page 168. And I hope you all are following along and really paying attention, so that when you get home, you'll understand what this lesson is about, so you can do your work this week. But notice the only thing that changed were the base numbers. So when the base was 10, all of them are raised to the x. But notice how the graphs, how they relate to each other. Notice that all of them are going to have asymptotes that approach on the negative side, they're approaching 0, right? Notice that all of them pass through the point 0, 1. Why is that, Miss Kim? Because any base raised to the 0 power will always be 1, right? We can plug that in our calculator. 10 raised to the 0 power is 1, just like 2 raised to the 0 power is 1. Therefore, they all join at that one point. But notice how some go up really quickly, and then how some are a little bit wider and they go up more slowly. What's the difference? Well, the larger the base, the faster it exponentially rises up, right? So notice how y equals 10 to the x is really steep. It's rising very quickly, because 10 to the first power is 10, but 10 squared, it's 100, right? It rises really fast. But y equals 2x, well, when I have 2 raised to the first power, well, friends, it's just 2, right? But then 2 squared is just 4. It still hasn't come close to the 10 yet. But exponentially, things eventually start snowballing, right? Like how a snowball, we started out small and it rolls faster and faster. So that's kind of what exponential functions do as well. All right. So they show you an example. The y equals 5 to the x power, the base is 5. So the asymptote will approach at the negative value, but 5 to the 0 power is going to be 1. They show you that in the first graph there, right below 23.2. And then notice how they do the next point. So then 5 to the first power, so you would do the 0.15. So they show you. So you really need 3 points to plot there on an exponential function. So maybe the -1, and then, of course, you'll always have the 0.01, because any base is raised to the 0 power is 1, and then whatever it is at 1. All right. Now notice on page 169, this time the base is a fraction. Well, when it's a fraction, it's going to do the opposite. So the asymptote, it's going to approach the x-axis at the positive side, and then the fraction is 0.25, or 1/4. So again, any base to the 0 power is 1. So I'm on the middle of page 169. So you'll see 0 is still 1. But this time, so all of our bases before, the asymptote was here. It was crossing the point, and then it was going up exponentially quick, right? So it started at the asymptote here, it crossed it here, and it went up. But we see the difference is when I'm looking at this, the asymptote is over here. This time the asymptote, and when it's a fraction, it's going to, so this is exponential growth. this is exponential decay, right? So we look at those two based on if the base is a fraction or if the base is a whole number. So we have looked at those in Algebra 2, but I know it has been a long time. So my friends, that is all that we're going to cover this week in Saxon Advanced Math. You're going to cover lessons 20 through 23, and make sure all of the boldface terms and anything written in boldface, make sure that's in your notes. You will receive extra credit for it, but it is also required because you in advanced math do not have any practice problems. So help me and make sure you're doing that at home, and I'll also reward you for it. Don't forget your assessment this week, and I'll look forward to seeing you all again next week. Thanks for your time and have a great week.